Hello and welcome back to the lecture on applied econometrics. So in this lecture we are going to talk about
autocorrelation, and in the previous lecture we introduced the concept of Darwin-Watson statistic. So this is essentially a test to detect if there is any significant autocorrelation in our model. In this lecture we are going to see the value, how can we get the values of Darwin-Watson statistic and gamma for positive autocorrelation and negative autocorrelation. We'll also talk about the limitations of Darwin-Watson statistic. We'll see that we cannot apply this statistic everywhere. So let's begin with the Darwin-Watson statistic for positive autocorrelation. So before we begin, let's recall that we actually introduced this formula where Darwin-Watson statistic and gamma are related. Now using this formula, we'll see what happens for positive autocorrelation and for negative autocorrelation. So let's first start with the positive autocorrelation. Now positive autocorrelation is something that is pretty common in economics problem. So let's write down positive autocorrelation. For positive autocorrelation, what would be our null hypothesis? Null hypothesis H naught is my gamma is equal to 0. So there is no correlation between the errors for tth period, between tth period and t minus 1th period. We remember we have already introduced this equation here. And whereas if the alternative hypothesis is going to be gamma is greater than 0. So for positive autocorrelation, gamma needs to be positive, right? So with this in mind, let me actually write down the equation that I've already written previously. So dw is close to 2 into 1 minus gamma, right? So now we'll fit some values here. So we know this is a correlation coefficient. Its value can vary between 0 to 1 for a positive autocorrelation. And if I fit the values here, what I'll see here, if gamma is equal to 1, I will see my dw value is equal to, so 2 into 1 minus 0 is equal to 2 into 0, 2 into 1 minus 1 is equal to 0. Whereas if gamma is equal to, let's say 0.9, which still signifies a quite strong positive autocorrelation, so my dw value is going to be, so 1 minus 0.9 is 0.1, 2 into 0.1 is 0.2. So that means my dw is going to have a smaller value. Now let's put gamma value on the extreme opposite. So if gamma is equal to 0, I will have 2 into 1 minus gamma, which is dw is equal to 2. Whereas if I put gamma is equal to, let's say 0.1, which is very small, so then I will have my dw statistic is equal to 2 into 1 minus 0.1, 1.8, right? So these are the different values we get. Now we can see that if the gamma, if there is significant positive autocorrelation, so gamma is 1 or close to 1, so my dw value is pretty low. Whereas if my gamma is, so if there is no significant positive autocorrelation, so what is basically gamma is close to 0, so then my dw value is going to be 2 or close to 2, which is pretty high. Now for all these cases, actually Darwin and Watson, they also provided us some tools to actually determine whether I can call the positive autocorrelation to be a significant positive autocorrelation. So what they provide is the du, or the Darwin-Watson statistic upper limit or upper critical, and dl, Darwin-Watson statistic lower critical. Now for positive autocorrelation, if we can see if dw is pretty low, 0 or 0.2, so then, or around that, so if on the other way, in other words, we can say that if dw is less than some lower critical, so let's say that dw here is, let's say 0.3 here, okay, so if my Darwin-Watson statistic is less than 0.3, then only I can say the positive autocorrelation is significant. Okay, so it makes sense, it is close to 0, so I have a lower critical 0.3 and my dw is less than that, so it is 0 to 0.3, so then I say that, well, there is a positive autocorrelation. Similarly, if there is a, let's say, upper critical, and let's say its value is, maybe it has to be 0 to 2, so let's say it is 1.8. okay, so if the upper critical is 1.8, and if my dw is, let's say, greater than du, so that's pretty high. So we have seen if dw is pretty high, so then perhaps my gamma is very low, so then that means there is no positive autocorrelation. Okay, so then I will say the autocorrelation is actually, there is no autocorrelation. Okay, so these are pretty understandable when the values are at the extreme. The DW values are at the extreme, so we can, using these boundary conditions, we can actually sort of decide whether I would call DW to be a significant positive autocorrelation or no autocorrelation. But if my DW value is in between, so let's say DW is greater than D lower, W naught sun lower, and smaller than DU. So basically, let's say DW is something like, in our case, let's say DW is 1. Now for this, if DW has to be 1, so in that case, my gamma has to be 0.5, right? So in that case, we cannot say very concretely that there is a positive autocorrelation. So what we do usually, if the DW value falls in between, we say that we cannot, conclude concretely whether there is a positive autocorrelation or not. Okay, so that's a kind of a gray area, right? So now let's talk about the negative autocorrelation part. In the same fashion, we'll write negative autocorrelation. For negative autocorrelation, again we'll use the same formulation where we'll have our null hypothesis, and for null hypothesis, like the positive autocorrelation, the gamma has to be equal to 0, so there should not be any correlation between ut and ut minus 1, so the gamma should be 0. Whereas the alternative hypothesis, gamma has to be less than 0 this time, because we are talking about the negative autocorrelation, so correlation coefficient has to be negative, so it has to be less than 0. Now again we write down the formula for Darwin-Watson statistic and gamma relationship. So dW is equal to 2 into 1 minus gamma, right? Now gamma here, now let's say, again let's fit some values. Let's say gamma is equal to, now in this case, the value of gamma will vary between, gamma is going to be, gamma is going to be greater than minus 1, and gamma is going to be less than 0, right? So let's first put gamma is equal to minus 1. So if gamma is equal to minus 1, that means a perfect negative autocorrelation. So that would mean the Darwin-Watson statistic would be 2 into 1 minus 1 is equal to 2 into 2, 4, right? It's close to 4. Or if my gamma is equal to, let's say, minus 0.9. So similarly, it will be 2 into 1 minus of 0.9. So it is going to be 3.8, right? So gamma value is going to, DW value is going to be pretty high. What if my gamma is actually 0? On the other extreme, if my gamma is equal to 0, my DW value is going to be equal to 2, just like what you have seen for positive autocorrelation. And if my, let's say it is pretty low, let's say gamma is equal to minus of 0.1, so my DW stat value is going to be 2 into 1 minus of 0.1, so 2 into 1.1 is equal to 2.2. So what we see here? We see here that if my DW stat is actually close to 4 or very high, so then I will say that there is negative autocorrelation. There is negative autocorrelation. Whereas if it is close to 2, we say that there is no autocorrelation. No negative autocorrelation. So we'll again use the same sort of decision rule to sort of decide whether there is a negative autocorrelation or not. So similar to the positive autocorrelation, here also we have the du and dl, which is you will get it, and this is created by Darwin-Watson based on the number of explanatory variable as well as sample size. So let's say in this case our d upper, let's say, is 3.5. Now if my calculated DW, if my DW is greater than D upper, okay, so let's say DW is something like 3.8 maybe. So what I'll say, I will say if this is the case, then there is a significant negative autocorrelation. So negative autocorrelation is present. All right. On the other hand, if my DW is lower than the D lower critical, if DW is lower than D lower critical, so let's say this value is, in this case, let's say it is maybe 2.2, okay. So if that is the case, if my DW is let's say 2.1, so then I will say negative autocorrelation is not present. Okay, so we can just match what we are saying here. So if it is lower than the D lower, so we can actually say that this value is pretty close to this. And similarly, if my dW is, let's say, lower than du and higher than I think dW is lower than du and higher than dl, so then we say that it is undecisive. Okay, we really do not know what is whether there is a significant negative autocorrelation or not. Now, one point that we need to be careful here. I mean, I have done it just for our understanding, but actually the du and dl, they are uh, calculated for negative autocorrelation. We have to see it slightly differently. So here, what we do is, I'll just explain it. The formula is something like this. So if if now let's say now let's use the same du and dl. Let's say for negative autocorrelation, let's say we have the same du and dl, which is now for negative autocorrelation, let's say we use the same du and dl. Du is 1.8 and dl is, let's say, 0.3. It is calculated based on the sample size and the number of explanatory variables. So my model does not know whether it is a case of positive autocorrelation or negative autocorrelation. So du and dl is going to be calculated in the same manner. Now remember that in case of negative autocorrelation, we have the value ranging between 2 to 4, right? So if it is between 2 to 4 and my du and dl is 1.8 and 0.3, we can't really make any sense, right? So that is why there is a little change made in case of negative autocorrelation, and that is, we say that if and we already know the highest for negative autocorrelation, the dw stat has a highest value of 4, and dw stat for negative autocorrelation, dw has the lowest value of 2, right? So it ranges between 4 and 2. Now for negative autocorrelation, how we create the decision rule is this. So if my dw stat is greater, if it is greater than 4 minus dl, if it is greater than 4 minus dl, now dl is a small quantity, let's say 0.3, and if my dw is greater than 4 minus 0.3, that is 3.7, and if my dw is something like, let's say, 3.8, so then I will say there is significant negative autocorrelation. There is significant negative autocorrelation. Whereas if my dw, on the other hand, if I see if my dw is lower, if my dw is lower than 4 minus d upper, 4 minus d upper, so what will happen? 4 minus d upper means it is going to give me a value of 2.2. So if my dw is less than 2.2, so that means dw has to be in the range of 2 to 2.2, right? It is given. I know that for negative autocorrelation, my dw value can range between 2 to 4. So if it has to be less than 2.2, it has to range between 2 to 2.2. So in that case, because I know that if my dw is close to 2, my gamma is actually close to 0. So because of this, I will say that there is no negative autocorrelation, no negative autocorrelation, right? Whereas if my dw stat actually falls in between, so then just like in the case of positive autocorrelation, I will have some gray area. I will not be able to say anything conclusively. So I will write it as, so if my dw is less than, if my dw is less than 4 minus dl, so that means if my dw is less than, in our case it was, I think we calculated 3.7. If my dw is less than 3.7, and if my dw is greater than 4 minus du, which is in our example 2.2, 2.2 and 3.7, 3.7. So let's say I have my dw which is, let's say, I don't know, 3. I have my dw which is 3. So that I will get from the formula, I can get dw is equal to 3 if it is 2 into 1 minus, let's say, minus a 0.5. Okay, so basically 1 plus 0.5, so that will give me 3. So if my rho is equal to minus a 0.5, I have my dw is equal to 3. So if dw is equal to 3, I will not be able to be very certain about the presence of negative autocorrelation. Okay, so of course the dw and dl will vary, so it might be a little, the you know the range the dw can take can vary, but that's essentially the idea. So in this case, we will say we are undecisive. We're undecisive. We're not sure about the negative autocorrelation. Okay, so that's basically how we understand and interpret the dw statistic, and how we use dw statistic to understand if there is any positive autocorrelation or negative autocorrelation. All right, now the last part of the lecture is essentially the limitations of dw statistic. So I will jot down some of the limitations, and I'll explain why the limitations, where from the limitations are coming from. Limitations of dw statistic. Let me explain the limitations. Okay, limitation number one. Limitation number one is that the DW statistic is applicable in AR1 process, and that was quite obvious. And I'll explain why this is obvious. It is applicable in AR1 process. AR1 process. Remember, when we wrote the equation, ut is equal to rho ut minus 1 plus some et. So this is essentially a representation of AR1 process. And when we took when we expressed the dw stat in terms of this formula, ut hat and ut minus 1 hat square, and in the denominator I had ut hat square, and I had this t is equal to 2 to t and t is equal to 1 to t. So I took only these two values, right? Ut and ut minus 1. I did not take ut minus 2, or I did not take ut minus 3, which would essentially mean my process would have been a AR2 or AR3 process. So because of these, essentially the Darwin-Watson statistic is applicable only for AR1 process, that we need to remember. All right, so this is one limitation. The limitation number 2 is that, and that is kind of quite intuitive, is that for different observations, the different UTs we observe, so all the regression equations should have the same y, same y and x's, same y and x's for all for all the for all the for all the different error terms, let's say. So all the UTs that we get, they should come from the same process. Okay, that is quite obvious, that is quite intuitive, so that is the second limitation. The third limit, so basically you cannot really change your models when you are estimating the error term. Now the third one is that we have to have the error term normally distributed. So that is normally distributed, be normally distributed. The fourth limitation of it is this: there has to be an intercept term. There has to be an intercept term. You remember when we wrote down this equation, we had this intercept term, okay? So there has to be an intercept term when you are estimating DW statistic, okay? And why is that? We have to have an intercept term, an intercept term, Now why you have to have an intercept term? Because if we don't have an intercept term, the error term will basically assume whatever is left, right? So then that is not what we want. So we want the intercept term to be there, okay? Now the fifth criteria, the fifth restriction is that the dependent variable, the lag dependent variable cannot be in the regression equation, okay? So regressors cannot include the lagged dependent variable. So that means it cannot have yt minus 1, yt minus 2, and so on. And why is that? Because we are trying to understand the relationship between ut and ut minus 1. Now, if I now introduce a yt and yt minus 1, the whole process will be somewhat distorted, right? So yt minus 1 will actually influence the equation, the relationship between ut and ut minus 1. So we do not want any of this to happen. So essentially, we have to be careful that we do not have within the x variables, the regressors, we do not want to have a yt minus 1 or any of the other yt's. So these are the limitations that we have to keep in mind when we are applying the Riemann-Rosen statistic. It is a easy to use and quite popular statistic, but we should be careful about these limitations. So with this, we'll end the lecture here. In the next lecture, I will talk about another process of identifying autocorrelation. Thank you.